Hello everyone, today we will learn about the application of graphs and properties of trigonometric functions. Firstly, let's review some of the content we have already learned. We have studied the graph of sine functions, and from the graph of sine functions, we can see the monotonicity, symmetry, and periodicity of sine functions. We have also studied the graph of cosine function, and similarly, we can see the monotonic interval, symmetry axis, symmetry center, and periodicity of cosine function from the graph. In the previous class, we have studied the properties of some functions using the graphs and properties of trigonometric functions, such as learning that y equals the absolute value of cosine x. Let's first transform the image. Draw a graph of the absolute value of cosine x and study the properties of the cosine x absolute value function based on this graph. Today, we will continue to use the graphs and properties of trigonometric functions to study some other problems. Let's take a look at example 1. Find the maximum and minimum values of the following function, or in other words, find the range of values of the function. Let's take a look at these three questions separately. Let's take a look at the first question. Y equals 1 minus cosine x, where x belongs to R. To solve the problem of the maximum and minimum values of this function, we only need to study the maximum and minimum values of cosine x on R to solve this problem. Let's take a look at the graph of cosine x. It is easy to see from the graph of cosine function that its maximum value is 1 and its minimum value is -1. So, that is to say, when cosine x is -1, 1 minus cosine x takes the maximum value, which is 2. At this point, x equals pi plus 2k pi, and k belongs to z. When cosine x equals 1, the function y equals 1 minus cosine x to obtain the minimum value, which is 0. At this point, x is equal to 2k pi, and k belongs to z. As you can see, by studying the graph of the cosine x function, we can obtain the range of values for cosine x, and thus obtain the maximum and minimum values of the function 1 minus cosine x. Next, let's look at the second topic, where y is equal to 1 minus cosine x. The range of x is the closed interval from 1/3 of pi to 2/3 of pi. Compared with the first topic, the range of x has changed, so how to use the image of cosine function to solve the problem of maximum and minimum value of this function? Let's take a look at the cosine x image first. It can be seen from the image that cosine x is monotonically decreasing at the position from 1/3 of pi to 2/3 of pi. That is, cosine x reaches the maximum at 1/3 of pi and the minimum at 2/3 of pi, so the problem of subtracting cosine x can be easily solved. Specifically, when x is equal to 2/3 of pi, the function y is equal to 1 minus cosine x to get the maximum value. At this time, the maximum value is 2/3. When x is equal to 1/3 of pi, the function y is equal to 1 minus cosine x, and the minimum value is 1/2. That is to say, we still solve the problem of the maximum and minimum values of this function through cosine x image and its monotonicity. Next, let's look at the third topic. Y equals 1 minus cosine x minus 1/3 of pi. The range of x is the closed interval from 1/3 of pi to 2/3 of pi. Compared with the first and second questions, our function expression has changed, which is replaced by x minus 1/3 of pi. So how to solve this problem? Because x belongs to 1/3 of pi to 2/3 of pi, we can first calculate the range of x minus 1/3 of pi. Specifically, when x is on the closed interval from 1/3 of pi to 2/3 of pi, the range of x minus 1/3 of pi becomes 0 to 1/3 of pi. In this way, we can solve the problem of the maximum value of our function by equivalently converting y to the maximum and minimum value of cosine x on the closed interval from 0 to 1/3 of pi. We still look at the image of y equals cosine x. What we are concerned about now is that the cosine function is monotonically decreasing in the range from 0 to 1/3 of pi. That is to say, at the point of 0, the cosine function reaches the maximum value, and at the place of 1/3 of pi, the cosine function reaches the minimum value. That is, when x equals 1/3 of pi, the function takes the minimum value, which is 0. When x equals 2/3 of pi, function takes the maximum value, and the maximum value is 1/2. Let's review these three topics again. In the end, the three topics solve the problem of their maximum and minimum values by using the images and properties of cosine functions. That is to say, we can use the image and properties of the function to help us solve the problem of maximum value. So, in addition to using the image and positive value of the function to solve the logarithm problem, what kind of problem can we solve? Next, let's take a look at example 2. It is known that the function fx is equal to cosine x, where x belongs to the closed interval from half pi to m. If the value range of fx is a closed interval from -1 to 0, find the value range of m. The value range of this topic is given, and what is required is the value range of m. So how can we use the image of the function and its properties to solve the problem of the range of m? First, let's still look at the image of the cosine function. Here, the plane x is taken from half pi to m. We don't know where m is. What is required is the value range of m. Through observation, it is found that in the range from 0 to pi, as the value of m increases, the cosine value corresponding to m slowly decreases. Now we need the value range of the function to be -1 to 0, so we let m continue to grow. When m reaches to pi, the cosine value of m is -1. At this time, the range from half pi to pi is exactly -1 to 0. Then let's continue to make m larger and see what happens to the value range. M is in the process of becoming larger. The minimum value from half pi to m is still -1. However, since m is now between pi and 3/2 of pi, the cosine value at this time is still negative and still meets the closed interval of -1 to 0. We continue to make the value of m larger. When the value of m changes to 3/2 of pi, at this time, the function value becomes 0. If the value of m continues to increase, you will find that the cosine value becomes a positive number, which does not meet the situation that the value range is -1 to 0.so. By observing the image, we can conclude that the range of m should be in the range of pi to 3/2 of pi. Specifically, by observing the image of cosine function, we can find that when m is in the closed interval from pi to 3/2 of pi, the value range of function fx is the closed interval from -1 to 0. You should find that using the image and properties of cosine function can solve the problem of m value range very conveniently and quickly. Then let's look at a thinking problem. It is known that the function fx is equal to cosine x plus 1/3 of pi, where x belongs to the closed interval of 1/6 of pi to m. If the value range of fx is a closed interval from -1 to 0, find the value range of m. Compared with example 2, the function in our theory changes from cosine x to cosine x plus 1/3 of pi. So how to solve this problem? We can still use a similar method. We first find the range of x plus 1/3 of pi from the range of x. That is, when x belongs to the closed interval from 1/6 of pi to m. X plus 1/3 of pi belongs to the closed interval from half pi to 1/3 of pi plus m. Next, we only need to deal with the value range of m when fx is equal to cosine x in the closed interval of half pi to 1/3 of pi plus m, which is -1 to 0. In this way, we have transformed our thinking problem 1 into the case of example 2. In example 2, we have found that the range of m is the closed interval from pi to 3/2 of pi. So for our thinking problem 1, the range of m should be 1/3 of pi plus m greater than or equal to pi and less than or equal to 3/2 of pi. From this inequality, it can be solved that m should belong to the closed interval from 2/3 of pi to 7/6 of pi. Next, let's look at question 2. It is known that the function fx is equal to cosine 3x plus 1/3 of pi, where x belongs to 1/18 of pi to m. If the value range of fx is the closed interval of -1 to 0, find the value range of m. Compared with the example and thinking question just now, the function in this question becomes cosine 3x plus 1/3 of pi. Then we can continue the thinking of question 1. We first find the range of 3x plus 1/3 of pi, and then find the value range of m. That is, when x belongs to the closed interval of 1/18 of pi to m. 3x plus 1/3 of pi is a closed interval from half pi to 1/3 of pi plus 3m. Then we only need to consider the case that fx is equal to cosine x in the closed interval from half pi to 1/3 of pi plus 3m, and the value range is -1 to 0. In this way, we turn to the case of example 2. In example 2, we have found that the value range of m is a closed interval from pi to 3/2 of pi. Therefore, m in our subject should satisfy that 1/3 of pi plus 3m is greater than or equal to pi and less than or equal to 3/2 of pi. We find that the range of m should be the closed interval from 2/9 of pi to 7/18 of pi. Let's compare these three questions again. Example 2, we solve the problem of the value range of m by observing the image of the cosine function and using the monotonicity of the cosine function. Thinking question 1 and thinking question 2, although our function expression has changed, we can both convert it to the case of example 2, and then find out the value range of m. We now use the image and properties of trigonometric functions to solve the problem of value range. Then let's take a look at how to deal with some inequality problems by using the images and properties of trigonometric functions. Let's look at example 3. Find the solution set of inequality sin x is greater than or equal to cosine x. How can we use images to solve the solution set of this inequality? Let's draw the image of sin x and cosine x first. The red one is cosine x image, and the black one is sin x image. To find out that sin x is larger than cosine x, we should focus on the black image and the parts above the red image. Note that we only need to focus on the case in the period from 0 to 2 pi, and then we can get the case in the whole r. In the period from 0 to 2 pi, we find that sin x and cosine x are equal at the position of 1/4 of pi. Next, sin x and cosine x are equal at the position of 5/4 of pi. In this section, sin x should be greater than or equal to cosine x. Then we have solved the case that sin x is greater than or equal to cosine x in a cycle. Of course, the critical point in this case is that sin x and cosine x are equal. So specifically, by observing the image of sine and cosine functions, we first calculate the solution of sin x equal to cosine x in the closed interval from 0 to 2 pi. Then we can get the solution of the inequality in the closed interval of 0 to 2 pi. That is to say, in the closed interval from 0 to 2 pi, the solution set of inequality sin x greater than or equal to cosine x is the closed interval from 1/4 of pi to 5/4 of pi. Then the solution set of the inequality sin x greater than or equal to cosine x should be x greater than or equal to 1/4 of pi plus 2k pi, and then less than or equal to 5/4 of pi plus 2k pi. K belongs to z. In the process of solving the inequality sin x greater than or equal to cosine x, we obtain the solution set of the inequality by using the images of sine and cosine functions and their monotonicity and periodicity. Next, we will consider such a question. Find the solution set of inequality sin x plus cosine x greater than or equal to 0. So, how can we use the image and properties of sine and cosine functions to solve the problem of the solution set of this inequality? We can first convert the inequality sin x plus cosine x to cosine x which is greater than or equal to 0, and then equivalently convert it to cosine x which is greater than or equal to negative. In this way, we draw the image of negative cosine x, and then draw the image of sin x. We can see what the result is by observing the image. Now we are drawing an image of negative cosine x. The red one is negative cosine x, and the black one is sin x. Similar to the previous example, we can first observe the solution set of sin x greater than or equal to negative cosine x in a cycle. Let's see. In this topic, it's relatively convenient for us to focus on the images within the period from negative pi to pi. In this period, we find that the point where sin x is equal to negative cosine x is negative 1/4 of pi and 3/4 of pi. That is, in the range from negative pi to pi, the point where sin x is equal to negative cosine x is found. Then sin x is greater than or equal to negative cosine x, which is the part of sin x image higher than negative cosine x image. Specifically, in the closed interval from negative pi to pi, sin x is equal to the solution set of negative cosine x. The solution of sin x equal to negative cosine x is negative 1/4 of pi and 3/4 of pi. Then in the closed range of negative pi to pi, the solution of sin x greater than or equal to negative cosine x should be negative 1/4 of pi to 3/4 of pi. Then on the real number set r, the solution set of sin x greater than or equal to negative cosine x is x greater than or equal to negative 1/4 of pi plus 2k pi, and less than or equal to 3/4 of pi plus 2k pi. K belongs to z. Let's take another look at example 3 and this thinking problem. In fact, example 3 can also be equivalently transformed into such a form. That is to find the solution set of inequality sin x minus cosine x which is greater than or equal to 0. Our thinking problem is the solution set of sin x plus cosine x greater than or equal to 0. In the process of solving these two inequalities, we use the images of sin x and cosine x and their properties. By observing the image, we get the solution set of these two inequalities. Next, let's summarize what we learned in this lesson. First, we use the image and properties of trigonometric functions to study the range of functions. Of course, in the process of studying the problem of function range, we do not have to use the function image, but we can also use the algebraic method. But in this lesson, we want to understand the image and properties of trigonometric functions and how to help us solve this problem. We use the image and properties of trigonometric functions to study the solution set of some inequalities. I believe you will find that we have solved some inequality problems by using the images and properties of trigonometric functions. That's all for today's class. Goodbye.